Well, thank you very much, Cecile. As Cecile indicated, Cassini was an incredible mission. We spent 13 years in orbit around Saturn, studying the planet, the rings, the many, many moons, and the dynamic magnetosphere, the bubble that's around Saturn. And then in September of last year, the mission ended as we plunged into Saturn's atmosphere. So I'm going to share with you just some of the incredible discoveries that we've made during that time. And when I think back on it, I've worked on the Cassini mission for almost 30 years. And that's the time it takes for Saturn to go around the sun one time. So I've worked on Cassini for one Saturn year. And when I first started on Cassini, my oldest daughter, Jennifer, had just started kindergarten, just started school. And now she's married and she has a daughter of her own. And that time has just flown by. And in a certain sense, my daughters have grown up with me and with Cassini. Cassini's findings have truly revolutionized our understanding of the Saturn system. We know so much more, building on the Voyager data that were collected in the 1980s. So I'm going to share with you a little bit about this picture that you see here is one of my very favorites. It's an eclipse picture. Saturn is covering up the sun, and you can see all of Saturn's rings glowing. And I'll talk about this picture a little bit more, but it's just a very incredible, kind of iconic picture when you think of the Cassini project and the ring system of Saturn. Now, a month ago, I was actually in Toulouse to give a talk, and I had a chance to go out to Carcassonne. And while I was there, I noticed that, Carcassonne is growing some of its own rings. And here's what I saw. That there were actually people putting looked like yellow plastic all over the sides of the building, and from a distance it looked like this. I'm thinking when they're finished, if you get to the right place, you might see these yellow circles arching around Carcassonne. Well, moving on to Saturn, where is Saturn in our family of planets? Here are the 8 planets in our solar system. You can see the 4 inner rocky planets, then Jupiter and Saturn are the gas giants, and the ice giants, Uranus and Neptune. Now, the planet sizes are to scale, but not the distance between them. Saturn is about 10 times further away from the sun than the Earth. And to give you an even better idea about the size of Saturn, here's the Earth and the Moon to scale, and the distance between them is to scale. And you could fit Saturn plus its rings in between the Earth and the Moon. So truly a giant planet. It could hold 764 Earths. Well, here's a view of the Cassini orbiter provided by NASA, and the European Space Agency provided the Huygens probe that parachuted into the atmosphere of Saturn's moon Titan. The Cassini spacecraft is almost 8 meters tall. If you look at that white high-gain antenna at the top, it's about 4 meters across. You can see some people there for scale. The Huygens probe is on the front there, bolted on, carried as a passenger on Cassini. Now at Saturn, we were so far from the sun, you'll notice there are no solar panels on Cassini. Instead, we used 3 radioisotope thermoelectric generators and used the decay of plutonium, the heat from that decay, to generate electricity, and that powered the Cassini spacecraft through the entire mission. You notice that Cassini has a lot of gold blankets. Often you'll see dark black blankets on a spacecraft, but we actually went into as close as Venus. So we had to have reflective surfaces to keep the Cassini spacecraft and the Huygens probe cool enough during that time. Now, as the Cassini spacecraft was being built, I'd go with this is my youngest daughter, Jessica, and we'd go periodically and we'd keep an eye on Cassini. At one time, they even let us put on these little suits and put us through the dust shower, the air shower, and let us stand next to the Cassini spacecraft. And so my family got to know a lot about Cassini. Now, as far as the names go, the Cassini spacecraft was named after Giovanni Domenici Cassini, and it turns out that he was born in Italy, but he came to France and changed his name actually to Jean-Baptiste Cassini, and he was one of the directors at the Paris Observatory. He discovered the gap you can see here, the Cassini division in Saturn's rings, and it seemed appropriate to name the mission after him. The Huygens probe was named after Christian Huygens. He discovered Titan. And so for a probe that would reveal for the first time the surface of Titan, it seemed appropriate to name the probe after Huygens. 19 different countries provided scientists, instruments, and operations for the Cassini mission, and the flags of those countries are shown here. And the international collaboration, I think, is one of the most wonderful aspects of Cassini, because it brings scientists together from around the world, and also it allows you to have a bigger mission because some of the funding came from Europe, some came from the United States, and so you could fly a mission as expensive and as ambitious as Cassini. Well, the Cassini project got started in 1990. That's when we picked the instruments, had our first Project Science Group meeting, and the Cassini mission was off and running. And so for those of you who remember back to 1997, 7 years later we launched, and here's a short video of the Cassini launch. Ooh, is there sound? I need to hook a sound port.
4, 3, 2, 1. Liftoff of the Cassini spacecraft on a billion-mile trek to Saturn. Pitch program is in, roll program is in.
Can you hear that? Okay. Yeah.
We have cleared the tower, and the Cassini spacecraft is on its way to Saturn. T plus 20 seconds. All systems are go. Jupiter Inlet Tracking Station now acquiring data. All systems go.
Cassini launched on a Titan Centaur. And I remember back in 1997, we took our daughters out of school for a whole week to go down and watch the Cassini launch, and they were thrilled because they got to miss a week of school. Then they got there and we said, well, I've got some interesting news for you. Cassini's launch is before dawn, pre-dawn launch. And so here's some teenagers that you're going to have to get up really early to go and see the launch. It actually took a couple of times because we had some problems with weather, et cetera, to finally launch Cassini. And I vividly remember that roar of the rockets as we're feeling the launch. And also as Cassini went into that cloud, the cloud got bright, and you could hear people kind of wondering, did the rocket explode? And then Cassini comes out, the rocket comes out the top, and Cassini was on its way to Saturn. Well, here's a view of the Cassini mission against the 30-year orbit of Saturn. So we launched in 1997. It took us 7 years to get there. We had 2 flybys of Venus, a flyby of Earth, a close flyby of Jupiter, each of those flinging us further and further out into the solar system. We arrived in 2004. We had a 2004 prime mission, and at the time, NASA gave us about an 80% probability that we could get through that 4-year prime mission, but everything went very, very well. That was followed by a 2-year equinox mission approved by NASA, and then a 7-year solstice mission. At the end, in the green box, we spent almost a year pulling in closer to Saturn than we ever had before with a set of ring grazing and grand finale orbits. Here's another view of the Cassini mission. You can see across the top the years of the mission. It shows you the orientation of the orbits. You'll notice that we had 127 flybys of Saturn's moon Titan. And we used Titan not only for interesting science, but also to change the shape and the orientation of our orbits. So in a very real sense, Titan was a tour driver and allowed us to do a lot more science in different views of the system without having to carry the extra fuel. We had 23 flybys of Enceladus. In the prime mission, we only had 3. But we made such remarkable discoveries about Enceladus that we added 20 more over the course of the mission. 15 very close flybys of some of the other icy moons, and then at the end, the proximal or grand finale orbits. And you can see the seasons changing. We arrived about 2 years after northern winter and ended the mission at northern summer solstice. Now, as a ring scientist, I'm intrigued by watching the shadow of the rings on Saturn. Because you see, the ring shadow is like a giant sundial. And if you can see the shadow of the rings, then you know the season. It's going to be fall or winter in the hemisphere where you have the ring shadow. So the top picture, the start of the mission, you can see the ring's shadow is in the north, At equinox, the ring is just a thin line as the rings are edge-on to the sun, and then as the mission progressed, the ring shadow moved to the south. One of the very early surprises was that Saturn's atmosphere in the north had a very bluish color. You don't see this hemisphere from the Earth, and so it looked very reminiscent of what you might see perhaps at Neptune, sort of that bluish color. The haze had basically disappeared. It was no longer forming without the sunlight, and you can see tiny Mimas in that picture. Here's a view of Titan and of Saturn itself, and you can see the rings edge on. You can see that bluish color is disappearing from the northern hemisphere as the sunlight is shining there. The haze is starting to grow again, the haze particles. And then the southern hemisphere, you can just see a little bit all the way off to the right there is getting that bluish color. If you look very carefully at the North Pole of Saturn, you'll notice that there's something unusual. Saturn has something in the North Polar region that's unique to Saturn. It's a six-sided jet stream called the hexagon. Why it has six sides and it has maintained them. It was first discovered by Voyager in the 1980s, and it's still there. Here's a view of that hexagon, and you can see that the haze particles haven't grown enough yet to make it golden color, but that jet stream is really a boundary, and the clouds race around the fastest on the rim of that hexagon. And here's a movie that shows you in false color what some of the cloud motion looks like. We were able to track and observe the hexagon, and also what Cassini discovered in the middle there, again in false color, was a giant hurricane. The hexagon's about two Earth diameters across. This hurricane is about 50 times larger than a typical Earth hurricane. It would basically span half the continental United States for this particular hurricane. The sun's coming in from the right, and you can see the shadow of the eye wall. Another spectacular finding at Saturn was this giant storm that started in 2010. Now, these storms on Saturn typically occur only about once every 30 years. This storm came about 10 years early compared to previous storms, and that put Cassini in conjunction with ground-based observers at the right place at the right time. In these filters with the cameras, you're really looking at the topmost parts of the clouds. If you go into the infrared, you start to look deeper, where here the greenish colors are looking deepest, and you can see an evidence of this vortex here, and that's what created this long tail. The tail wrapped itself around, and when the vortex in the head met a vortex in the tail, that marked the end of the storm about 9 months after it had started. Now, if you look at even longer wavelengths in the thermal infrared, this is basically looking at the troposphere. If you look at the stratosphere, a tremendous amount of heat and energy went into the stratosphere. And this is from Sears data, and you actually saw some new chemistry going on in the atmosphere of Saturn. Moving on to the rings themselves have very simple names. The main rings, the A ring, B ring, C ring, and D ring. Then you jump out to the E ring, the tiny F ring, and finally the G ring. And we knew about the main rings going all the way back to Galileo, but the E, F, and G rings were discovered much later. Here's a beautiful color view of the rings of Saturn. They're made mostly of water ice and particles that range in size from some very small, almost dust grain sized particles to the size of marbles to some particles that are even building or mountain sized in the rings. But most of them tend to be in that centimeter-ish size range. And you can see the Cassini division very clearly. There's another gap, the Encke gap, in the outer part of the A ring. And most of the material of the rings is in the brightest ring in this lit view, the B ring. Here's the rings edge on to the planet, and it's just amazing. For a few days, the sunlight didn't fall on the rings, completely turned off. And for this particular mosaic of images, the rings were brightened by about a factor of 20 on the left and by a factor of 60 on the right, so you could see them in this particular mosaic. And this is a wonderful time to look at the rings, to look for anything that sticks up above or below the rings. We were trying to see were the rings tipped or tilted, warped in any particular direction. And it gave us a chance for the first time to sound the three-dimensional structure of the rings. And one of the things we found at the edge of the B ring, the thickest and brightest ring, were a lot of shadows. You can see all of these spiky shadows here coming from objects that are much larger than the on average about 3 meters thickness of the rings. So these objects are much larger than that, and they stick up and they cast shadows. And you can see that there are hundreds of them, jammed like cars on a crowded freeway on the outer edge of Saturn's B ring. Cassini also discovered a bump on the edge of the A-ring, a brightness of material, and that appears to be associated with the birth of a small, tiny moon. That moon was nicknamed Peggy. The discoverer, turns out it was his mother-in-law's birthday, and her name was Peggy. So she got a moon nicknamed after her. We've been watching Peggy ever since its discovery in 2013, trying to see if Peggy would break free, become a satellite of its own, or perhaps go back into the rings and be broken apart again. It's made probably of ring particles. Even to the end of the mission, we could still see hints of Peggy right there at the edge of the A-ring. Here's this picture I showed you earlier. Saturn is covering up the sun. And just point out a few things. If you look carefully, there's a white ring around Saturn. And that ring is every sunrise and sunset on Saturn at the same time. You can also see the night side of Saturn isn't completely dark. The rings are lighting up the night side of Saturn, and that's what you're seeing going across it. These are all tiny particles. If you've ever had a really dirty windshield and you drive into the sun, the tiny dusty particles tend to send photons or light into your eyes, and the same way we're looking at the forward scatter or the light coming through the dustiest part of the rings. Now, if you look carefully, there's also other planets besides Saturn. Turns out that Mars, Venus, and the Earth and the Moon are in this picture as well. And we actually spent about 20 minutes, there's the Earth on the left and the Moon, taking pictures of the Earth. We knew ahead of time. So we told people, go outside, wave at Saturn, and photons from you will go up and become part of Cassini's picture. And so it turns out it was nighttime in Europe, and then it was just daytime on the west coast of the United States. So this huge swath of the Earth, people went out and waved, and we said, now we know we're not going to be able to see you in a Cassini picture, so take a selfie and send it to us, and we'll put those together and use it. And so we got pictures of families and people holding up their dogs waving and babies waving. We just had all sorts of people. So we did. We recreated this mosaic out of thousands of selfies that we got. And I'll tell you, this was one of our most popular websites to go to because people wanted to know, where am I in this particular mosaic? And I did the same thing. I kept hunting through row by row until I found where Tom and I were in this particular picture. A little bit about some of the moons. You can see Saturn's moons. There are 62 of them. Many of them are in the outer regions of the Saturn system, and they're captured objects, maybe captured centaurs, Kuiper belt objects, etc. And just to give you an idea, that big moon Titan is about the size of the planet Mercury. And if Titan had formed anywhere else in the solar system, it would have been a planet. I think this picture is so intriguing. Here's this moon, Iapetus. It's the third largest moon of Saturn, about 1,400 kilometers in diameter. And it has this huge ridge or belly band on it. And also it has one really dark side and one really bright side. And that ridge is intriguing because one idea is maybe the ridge was formed when Iapetus had a ring. And as that ring decayed away, the particles fell along the equator. Perhaps it formed a ring. There are other ideas as well. But it looks like a walnut shape. That ridge is over 20 kilometers high. That's about 3 times taller than Mount Everest. And you can see that it's just old because it has a lot of craters, and a lot of material that fell on top of it and eroded it away. Near the end of the mission, we got pictures of these 3 tiny, what we call ring moons, because they're in close to the rings. And it just was amazing to look at them. Atlas orbits out here out of the edge of the A-ring. Then you have tiny Daphnis in the Keeler gap, and Pan orbits. You can even see Pan right here. This in the Encke gap. So it's just as amazing. What you notice is that these moons have accumulated a skirt or a giant ridge of ring particles. And it's mostly around their equator. Probably an icy core and then a mantle of ring particles. Even tiny Daphnis has what appears to be a ridge on it. So this getting in close to Saturn gave us our first opportunity. We got some great Sears data on some of these moons as well. And I really love this picture. This is Daphnis in the Keeler Gap, and Daphnis creates a wave along the edge of the gap, and as you watch the wave going further from Daphnis, it actually appears to be separating. Daphnis has a slight inclination, so it pulls the particles not only horizontally but vertically out of the plane as well. And there's even a little tiny piece of the ring that Daphnis's gravity has pulled away. This is Voyager's view of Titan. We didn't have any instruments on board Voyager that could probe through and see the surface. And so in the early 1980s, after the Voyager flyby, a series of scientists got together and said, we need to go back and take a probe so that we can go down through the haze and see the surface of Titan. And the fathers of Cassini were Daniel Gaudier, Wing Ip, and Toby Owen. And together they formed a collaboration across the pond, across the ocean, to try and get the mission that was called Cassini, and they were successful. And this is an artist schematic of the release of the Huygens probe. Had to, of course, decelerate with the heat shield, and then using a series of parachutes, spent about 2.5 hours sampling the atmosphere, its composition, its temperature, its pressure, and then landing softly on the surface of Titan and continuing to send back data. Cassini was flying overhead, and Huygens was relaying the data back. Once that was over, Cassini turned to the Earth and sent the data back down. And here's a movie taken. We had cameras on board Huygens as it was spinning, and so in this movie you can see the Huygens probe getting ever closer to the surface of Titan. We saw what looked like river channels on the surface, evidence of dunes in the distance. It was great as we pierced through the haze, and then finally a soft landing on the surface. Huygens was built to float because we weren't sure if it might be covered with an ocean of liquid methane. And here's the probe landing, and we got a series of pictures over about the next hour or so of this particular spot. We actually saw the shadow of the parachute move through the field of view. And on Titan, methane plays the role that water plays on Earth. You can have methane clouds, methane rain. Methane can carve river channels and fill lakes and seas. And here's a view again, the color view. We had a lamp. You can see the spot of the lamp here to allow us to get true color on Titan's surface. There's an idea of some of the sizes of some of those icy pebbles. And just to show you as you look toward the horizon with Huygens, it's kind of like here, there's a footprint on the moon. You can see a little astronaut at the top there. And here are just one of the snapshots of the river channels coming down. Looks like we landed in a dry stream bed or lake bed on the surface of Titan. This is Titan, and if you look at the North Polar region, you'll notice there are a lot of black splotches. It took a while for it to become light in the North Polar region. We did have radar data, and we wondered, of these lakes and seas, do they have liquid or not? It turns out we looked for something called a specular reflection. This bright spot here, when the sun comes in and hits a liquid at just the right angle, Cassini is looking at that same angle, then you can see that specular reflection. So we knew there was indeed liquid in the lakes and seas on Titan. And here's a radar view of one of those lakes, Ligeia Mare. It's about 50% larger than one of the Great Lakes on the Earth, and you can see the tributaries and the river channels going into it. So what we saw, Titan was very Earth-like, lakes and seas and river channels. At the equator, dunes made of these hazy particles that were keeping us, for Voyager, from seeing through to the surface. Mountains and possibly cryovolcanic flows on the surface of Titan. In false color, one of the methane clouds and some of the weather that we saw. And then, of course, an example of a dry riverbed. We landed more toward the equator than toward one of the poles. For the moons, I just want to end up with this very incredible tiny moon, Enceladus. It's only 500 kilometers across, about 1/10 the size of Titan. And we thought certainly this moon should be frozen solid. It's so small and so tiny. But we knew from Voyager that the surface was very bright. We also knew that it was in the center of the E-ring and somehow was providing material to the E-ring. The South Pole was dark when the Voyager spacecraft flew by Enceladus, so we missed the biggest clue right here. 4 linear fractures nicknamed tiger stripes. Turns out the first clue that Enceladus was an active world actually came from the magnetometer. instead of the magnetic field lines going down to the surface, it turns out they were standing off in a way that was reminiscent of a comet. And so there appeared to be some kind of a neutral cloud or activity coming out of the south pole of Enceladus. Another clue came from the Sears data. The south pole was much hotter than it should have been if Enceladus was in thermal equilibrium. And so this shows the hot spot at the south pole. And then as the mission went on, we got closer, we could actually see the heat was coming from those 4 fractures at the south pole. Here's a close-up of one of those fractures. They tend to be about 130 kilometers long, a couple kilometers wide, and they have generally 2 ridges on either side. And here it almost looks like there's a frost or something on one of those ridges. And with our images, we saw that there were actually geysers coming out of the South Pole. 100 of them, individual sources of water vapor and water ice particles with many other interesting constituents. And here's another view. You can start to see the individual jets coming out of the South Pole of Enceladus. This view is in backscattered light, or in forward scattered light. You can see now the individual jets. Also found not only did they have water in them and water ice, but also some of the grains were salty. And this told us that the liquid water reservoir, the ocean underneath the icy crust, was salty with a pH, we think, in a range very similar to the Earth's oceans. We found organics all the way across the scale for our ion and neutron mass spectrometer, complex organics, coming out of these jets. And we actually flew 7 times through them, tasting and sampling and making direct measurements of their composition. Now, it turns out that we have an Enceladus here on the Earth. It turns out if you go to the gardens at Versailles, here's the Enceladus fountain. It turns out Enceladus was a giant, and he got into a bit of trouble with Athena, and so she made sure to cast him down, and he got trapped at Mount Etna. And so here he is with a 25-meter-high stream of water, like a giant geyser, coming out of his mouth. And so it just was interesting. I took this picture, and great to see this Enceladus. That black dot in this image is Enceladus, and you can see here the plume from the jets and wispy fingers of particles. Most of the particles fall back to the surface, kind of like snow. Imagine standing on Enceladus and putting your hand out near one of those geysers, and you'd get like snow falling back. The very tiniest particles escape Enceladus's gravity and go on to form the E-ring. And if the Enceladus geysers turned off, probably in 100 years or less, the E-ring would disappear. They're made mostly of tiny particles that get moved around by the sun, and they can get charged by the magnetic field. So it really, Enceladus is keeping those particles going. Here's a schematic showing Enceladus that's differentiated. It has a rocky core, and we have evidence with the excess of hydrogen in particular coming that there's hydrothermal vents, most likely on the seafloor, which is really incredible because you have this ocean that's salty, filled with organics, and now you have a source of heat energy. And if you look at the Earth, there are hydrothermal vents on the Earth. If you look deep in the seafloor spreading regions where there's no sunlight, you find evidence of these white smokers. The water goes down and is heated up inside the Earth's crust. When it comes back out, it releases the minerals that it's picked up, and it looks like smoke, like a giant forest fire. And we've taken submarines down to look at these ridges. And when you get in close, right around these hydrothermal vents, it's teeming with life. Tube worms and little crabs and all kinds of very interesting life in an island around these hydrothermal vents. So it makes us wonder, could Enceladus perhaps have life? Could perhaps ocean worlds, we know Europa has an ocean, Titan has a liquid water ocean, other moons, could life form underneath the icy crust at these places so far from the sun that their surfaces are frozen? Just a little bit about Cassini's end of mission. This is a view of the Cassini spacecraft. Actually, for the first time, we took the spacecraft in between the rings and the planet. And we had some very clever navigators. When we first launched, we didn't know we could do this. And they found a way using a single close flyby of Titan with the orbit in just the right orientation to, in a single orbit, go all the way across the rings and go down in the gap in between them. It's about 2,000 kilometers wide. So here's a view of the orbits, 22 orbits flying in between that gap. We picked an orientation where the closest approach was around noon This gave us really good gravity data and also good views of the rings and the planet up very, very close. These orbits were about 6.5 days long, and so it was a very intense, very busy period. Now you'd think 22 orbits, you can do a lot. I think we wished we would have had 22 more, because it was really hard to decide how to share that time in very, very close to Saturn. That final red orbit is that orbit that will ultimately take us in to the planet itself. The orbits moved around a little bit because there would be distant flybys of Titan. And on that final orbit, we got what we called the Titan goodbye kiss that sent us then into Saturn. Now, if you could ride along with the Cassini spacecraft, maybe sitting on that white antenna, what would it be like? And here's a little movie that's put together. It's just an hour or so compressed into about 15 seconds. You go very quickly through that gap between the rings and the planet and on out again over and over for 22 orbits. And I'm a big Star Trek fan, and I wonder what it must have been like, if you could take the Enterprise and go diving through this gap between the rings and the planet. Just show you a little bit of the data that we got back. This is from the first orbit, taking a series of images. That red dot shows you where we are on the planet, and we're getting closer and closer and closer as we go through the gap, seeing more and more detail in the clouds themselves. Now you'll see that frame rotate in just a minute. We weren't sure what we'd find in between the gaps, so we actually rotated, turned the high gain antenna down like a giant shield to protect us until we could find out how many ring particles were in that gap and how big they might be. And so it's just really a wonderful chance to view Saturn. Here's some little wispy clouds. Some of the Saturn scientists said they'd never seen anything quite like it. And so we had a couple of scans like this to look in detail at Saturn itself. In getting very close to Saturn, we were actually able to get the mass of Saturn. From the orbits outside, we had the mass of Saturn in the rings, and by looking at the two data sets, we could then finally get a mass for Saturn's rings. And that's key because massive rings could be old, perhaps as old as Saturn itself. Less massive rings probably couldn't have lasted since Saturn formed, and so you need an event that forms those rings. And it turns out that the Voyager value, if you could scoop up all the ring particles, it'd be about 3/4 the mass of Mimas. And with Cassini data, we found it was actually even a little bit smaller. So that tells us for the first time that the rings are young, perhaps 100 million or a few 100 million years old. Dinosaurs roamed the Earth, perhaps, when Saturn's rings in their current form formed around Saturn. And just incredible to see this and all this just from these special orbits. We couldn't have gotten the mass without these grand finale orbits. We got so close, we could see the rings at a level of detail we'd never, ever seen them before. And what we notice that there's places in the rings. What you can see is the image of the rings, and then here, what's been subtracted out is sort of an average, and anything that looks streaky is where there's azimuthal structure. It's not uniform along that particular plateau or ringlet. What was most surprising is it was different kinds of textures: streaky texture, clumpy structure, feathery structure, all these adjectives we had to describe it. But more incredible is that there were places, very narrow places, where it seems like there was azimuthal symmetry, no structure. So in very short distances, the character of the rings changed. And we're still thinking about how could this happen? What's going on in Saturn's rings to cause them to clump up? And why do they clump in some places and not in others? Here's a view, a summary of what we found in between the rings and the planet. There's basically a dust band of very tiny particles. The good news is that most of the particles were nanograins, and even at the speeds of Cassini, that didn't do us any damage. So a dust band here. Then there's a region where you're transitioning from the ions and neutrals coming from the rings into the exosphere, and here's the ions and material coming from Saturn, and they're mixed in this region. And so it's very interesting, very different than what we had expected. Here's the cosmic dust analyzer data. Here's a model of what they saw. Here, this white trajectory is for a ring particle. They saw most of the ring particles right at the crossing at the plane, but some of those actually get charged up and come from the other rings as well. They basically saw two types: silica particles and water ice particles. And so really for the first time directly sampling the composition of the ring particles. Now the ion and neutron mass spectrometer, which usually measures gas, actually measured particles that vaporized inside the instrument. And what they found was truly astonishing because they found a more complex spectrum than they saw either at Enceladus or at Titan. That there's a whole host of organics present all the way out to the limits of their resolution, 100 atomic mass units, of course hydrogen and various components. And so these were just a direct sample of the ring particles. Now just a day or so before we went into the planet, we took this final farewell image to the Saturn system. And it looks like Saturn is just sort of floating like a giant ball inside the rings. And this was really a difficult day to say goodbye to Saturn. And so here's a view of the people applauding, hugging, just a lot of emotion. Cassini was an incredible mission, and just everything worked so perfectly. And yet it would be great to have had another 10 years for the Cassini mission. And here's a view of the Cassini family taken at JPL, all of us waving goodbye to the Cassini mission, and knowing that chance to see Saturn was closing. That window was closing until we get a chance to go back. And I had an opportunity to share this experience with my daughters and with my granddaughter, Audrey. So they were there with me as well to witness Cassini's grand finale. And I want to show a very short video. This is some of the pictures that we got back set to music and is a part of Cassini's legacy. When I see that movie, I think I want to go back. Thank you very much. I'd be happy to take any questions. Okay.
Questions, comments? Be the first one. So maybe I can just start. You are talking about storms on Saturn. Is this water, methane? What are they made of?
The storms on Saturn, there's some methane there, but there's ammonia clouds, hydrogen sulfite clouds, different things that could go into form it. Depends on the level of the atmosphere, what exactly will condense out. Saturn's mostly hydrogen, so what you're seeing is just mostly hydrogen with just a little bit of other constituents that give it its color and its cloud dynamics.
Linda, I didn't ask you this question before, but are you keeping track? Does Cassini have new discoveries of rings, even tiny ones, or satellites? Has it increased the number of the satellites, little moons we knew, or?
Cassini did discover some additional new tiny moons, about half a dozen of them, and we found that lo and behold, a lot of the smallest moons actually have rings or partial rings associated with them. So Pallene has the Pallene ring and so on. So there were new rings and moons discovered by Cassini. And then ground-based observers keep discovering the moons typically in the outermost part of the Saturn system. And we got some really great views looking at the rotation and phase angle for those whole suite of captured objects that are in the outer part of the system. And in fact, one of the moons, Phoebe, is in an inclined retrograde orbit, and it's the source of the dark material coming into the system on Iapetus. So.
You have to say more about the origin of these young rings.
Well, I mean, it was a puzzle. With Voyager first arriving at Saturn in the 1980s, the rings were bright, and the assumption was they hadn't been polluted very much, and so the thought was that they were young. We had estimates of the mass from these waves in the rings called density waves, but the B ring was so thick that the occultations and the measurements that could give us mass couldn't see through that ring, and so we were kind of left with the open question, is there a lot of mass hidden in the B ring? Because it's so optically thick, and so we have a new puzzle. The B ring is not very massive, and yet it appears so optically thick. It might not be much more massive than the A ring, so how can the B ring show us such a very different character? We have other evidence. The cosmic dust analyzer actually looked at the pollution rates for the rings and got a better measure of the micrometeoroid bombardment, and they too see evidence for young rings. So we have both the mass as evidence, the brightness, and now the amount of micrometeoroid bombardment kind of all taken together. And there's a couple of papers, one in Science, I think one in Nature, that should be coming out soon.
This may be a very naive question, but what makes that some planets have rings and others not? And what is it, the meteorites, the position with respect to the sun, the atmosphere, and what comes out? Or
yeah, what makes rings? That's a really good question. What planets get rings? Turns out all four of the outer large planets have ring systems of some sort. But now we have objects like Chariklo that also has a pair of rings. So why sometimes you get rings and you don't? I think the inner moons, perhaps, a lot of the material, if you have a moon like the Earth, it's going to be very hard to have a stable ring. And those planets are much smaller. But that's a good question. How come Chariklo has rings? And at some point we can look for exoplanets and maybe increase our statistics and see what kinds of exoplanets might have ring systems as well, because they'll look very different from just a planet itself once we get much better telescopes and ways to look for them.
So you mentioned the activity on Enceladus. Is it totally ascribed to tidal heating by Saturn? And my other question is, has it lasted since the birth of Saturn, or is it a recent phenomenon?
Yeah, the tidal heating, originally we thought there wouldn't be enough tidal heating. Like Io, there's enough heating to squeeze it, and it has active volcanoes. But finding a liquid water ocean, we found that from the libration. Enceladus librates back and forth a little bit as it orbits Saturn, and the libration was great enough that you needed to decouple the ice crust from the rocky core, leading to a global ocean. As far as how long the activity's been going on, that's a very interesting question. Now that the rings are young, there's some models that perhaps the inner moons of Saturn maybe out to Dione, maybe even Rhea, might be young as well. Maybe there was some kind of a catastrophic event in the system that disrupted the system, the inner part of the system, allowed the rings to form, and perhaps took the pieces and formed the moon. So now the question is, how old is Enceladus and some of the other inner moons? And so there's some competing ideas now about that.
Has Enceladus been dated by crater counting?
There's been some work, yes, with crater counting. Enceladus is particularly difficult because you've got material that falls back onto the surface, and so most of the surface is probably quite young. That's a little older, maybe in the North Polar region, but certainly, perhaps Iapetus, for instance, it looks pretty ancient, didn't change in any way, but there's some question marks now. Different theories, depending on what the state of Saturn might have been too, for those inner moons. They don't look like the Galilean satellites, which have a very regular pattern in density as you go out from your primary Jupiter. In the Saturn system, that's very different. The densities and what they look like are quite different. That's part of the puzzle. It doesn't look like what we expected. So I think we're just learning to ask better questions.
May I ask another question? On Titan, did you actually see some release of methane from the interior, or is somewhat constant, whatever is very constant?
On Titan,
Yeah.
we didn't see an increase in methane in the atmosphere that would indicate there had been some kind of we think maybe a cryovolcano, water mixed with ammonia might be one mechanism to bring methane to the surface. And it's interesting because we know that the methane at the top of the atmosphere is broken apart by sunlight. And if you don't replenish it from below, that methane will slowly disappear with time, and the effects of basically a giant greenhouse, the atmosphere of Titan will collapse. And so we didn't see an increase in the short time that Cassini was there, but there are some hints of perhaps cryovolcanic flows at some point. One idea is perhaps the methane is trapped in clathrate cages underneath the surface, and you just have to bring that clathrate out to release the methane. But there's reservoirs, big reservoirs there in the lakes and seas. It's about 100 times the hydrocarbon reservoir of the Earth. So there's a lot of ethane there.
Okay. Do you have more questions, comments? If not, let's thank the speaker once again. Thank you.